Hello everyone, my name is Oksana and today I present the short paper, Preserving Contextual Information in Relational Matrix Operations. First of all, let me state the problem we want to solve. We want to integrate complex analytics in relational databases. It means that we want to perform the combination of relational and matrix operations. Consider the examples of such combination. This is the inversion followed by a join and multiplication followed by a selection. We want to apply such operations to relations stored in databases and that include not only numerical but also contextual information. Contextual information includes schema and some attributes in the relations, and it describes the numerical values. This is not the first attempt to extend relational systems with linear algebra, but in our work, we focus on the processing of non-numerical values and schema in input relations during the matrix operation computations. Let's proceed with the application scenario. The example relations store information about a plant bakery, and relation shift records information about shifts. For example, tuple S1 states that on March 21st, 2019, 4 workers were working a 10-hour shift. Relation fault stores the scrap percentage of different machines. For example, tuple F1 states that on the same day, the scrap of mixing machine MM1 was 1.2%. Finally, the relation profit stores information about selling baked items, and tuple P1 states that on the same day, 53 items of Moscow bread were sold with a 5% of rebate and a total profit of $6,100. In the year to come, in the year 2021, the schedule is changing, introducing shorter shifts and increased number of workers. Please look at the tuples S3 and S4, and you see that the number of hours is increased and the number of workers decreased and increased. The task is to predict the monthly profit in the year 2021, taking the adjusted schedule into the consideration. So basically, we want to find the values in those cells with the question marks. Typically, tasks with prediction of certain values are solved by regression. In our case, this is a linear regression that calculates the impact of shift length and fault on the profit. Once calculated, those coefficients can be used to estimate the profit based on average fault and shift length in 2021. Besides of linear regression that requires matrix operations, relational operations are also needed to perform, first of all, data preparation and aggregation, because the number of entries per day in relation S and P is different. So in S, it's 1 tuple per day, and in P, several tuples per day. To solve this task, we propose relational matrix operations that preserve contextual information. So what is the contextual information? Please consider matrix M and try to answer to the question what is the meaning of value 70 in matrix M. Value 70 in matrix M does not have any context and cannot be really described. Besides its position, it's located in the second column and in the second row. Now consider relation profit and try to answer to the same question about value 70. Value 70 in the relation P has a crisp meaning. This is the number of raisin cakes sold on March 21st, 2019. Blue, violet, and cyan values of relation P provide this information to us. We call these values contextual information. Contextual information describes numeric values in relation. Contextual information defines a unique position of numerical values. And contextual information connects relation P with the relations S and F by attribute D. Thus, contextual information is an important part of a relation and should be considered in matrix operations that are generally defined only over numerical objects. So we extend relational algebra with the relational matrix operations. For all basic matrix operations such as inversion, matrix multiplication, element-wise operations, decompositions, we define corresponding relational matrix operations. They are denoted with small letters. The key properties of our solution are the following. All relational matrix operations have the precise definitions. All relational matrix operations take as input and return relations, such that RMA, relational matrix algebra, is closed. And all relational matrix operations preserve important contextual information in result relations in a principled and systematic way. We consider a few examples of relational matrix operations, but let's start with the structure. So here you can see the relational run computation, the relational element-wise addition, and relational matrix multiplication. All these operations have the following structure. The name of the operation, 3 letters, then the input relation or input relations in case of a binary operation. And for each input relation, the list of attributes like U or U and V in binary operation is specified. U is a part of contextual information, and it determines the order of tuples before applying matrix operation. Matrix operation, corresponding matrix operation, is applied to the values of the complement of U of the wide area ordered by U. Result relation is composed of the result of the corresponding matrix operation, and it also includes contextual information of the input relations. So let's look at the concrete examples, and let's start with the relational matrix inversion. This is the formula for relational matrix inversion. It looks a bit scary, but it just defines how exactly the result relation of relational matrix inversion is composed. This inversion is computed over values in attributes E and H of relation R ordered by T. In formula, this white part is denoted by complement multi R. So how the result relation is composed? First of all, it includes the matrix result of inversion applied to complement multi R. These values, they are different from the input relation. And also the contextual information is added. Here the multi-R, TR stands for ordered values of attribute T. Here they are ordered. And of course, the schema. The schema is in the result relation is the same as the input relation. Because inverted matrix has the same cardinalities as input matrix, the relational inversion preserves the entire contextual information as is. But this is not always the case. The next example of relational matrix operations is the crossproduct, and crossproduct is the result of multiplication between columns in input relations. So consider the crossproduct between values in EH ordered by T and values in JK ordered by F. This is the notation. For example, value 20, this is computed as ordered values of E multiplied by ordered values of G, and this is how it's computed. This is the formula. Unlike in relational inversion, contextual information of input relations is not taken as is, but must be adjusted for the computation of cross product. The new attribute C is added, and it includes the attribute names of R, E, and H, and it gives meaning to values in white part. Because, for example, 20 is computed with the column E and column G, and C helps to describe the connection between E, G, and 20. So now we have considered the approach, and let's look how our application scenario can be addressed with our approach. The task requires 3 steps to perform: to prepare the relevant data for the linear regression computation, to compute the linear regression between machine fault, shift length, and the profit, and to apply this knowledge for the future values to estimate the monthly profit of 2021. Let's start, the first step, the data preparation. This is an important step in typical analytical computations. This step is required to perform standard relational operations. And for example, relational operations such as aggregation or join are performed to compute U1. U1 stores the average fault and shift length per day. Aggregation is also used to compute U2, and U2 stores the profit per day. Once we have U1 and U2, we can proceed with linear regression. And having relational matrix operations help us to solve linear regression over relations. To compute linear regression, we use the simple ordinary least squares formula, where A is a matrix with the length and fault, and V is a vector with the daily profit. So look at the formula and the corresponding RMA expression. There is a direct connection between them. And for example, orange matrix cross product is mapped to relational orange cross product. So now look at the result relations and the final result of linear regression computation U6. This is a good result relation because it has a proper schema and it has a non-numeric attribute V. Because of these values, we can say that 144 denotes the number of dollars decreased from the profit for each % of scrap. Contextual information in U6, namely profit, var, and fault and length, is preserved through a chain of relational matrix operations. For example, the blue and cyan parts, var, fault, and length, they are taken from relation U4, the first operand of matrix multiplication. In U4, they are taken from relation U3, and in U3, they are coming from a schema of U1. So finally, the last step of computation, the profit estimation based on the result of linear regression, this U6. The linear regression result is multiplied with the corresponding length and fault in 2021 to predict the future profit. While the shift length in 2021 is given, and we just need to select the proper values, proper tuples, the fault in 2021 is not given, of course, and we estimate it by taking the average fault in 2019. So this is the true example of a combination of algebras. You have a selection, you have a Cartesian product followed by a relational matrix multiplication, and followed by an aggregation again. We also offer SQL extension for the relational matrix operations, and this is how the SQL extension for the relational matrix inversion looks like. It includes the name of the operation and the by keyword. The by keyword specifies the ordering attributes for the purpose of inversion, and the rest of attributes are used to compute the operation. Consider this figure. This is the SQL expression that computes U5 relation, and this is the cross product, computes cross product between the average fault and length of shift per day and the total profit per day. The SQL extension is simple, and new queries that require the mixture of algebras are easy to construct. If you want to know more, or if you want to try out the implementation of selected relational matrix operations, please go to this link. So we proposed the relational matrix operations. They are working with relations, and they preserve contextual information. And so our approach performs queries that combine relational and matrix algebras. Thank you for your attention. And if you have any questions, please contact us by this email. Bye.